Yep, so as Denise said, I gave a talk in Milan about MimbleWimble about a month ago. And this is more or less the same talk, but it is rebalanced a bit to try to emphasize what I think is important and add some history that has happened in the intervening time. So I'll get started. So many of you have heard of MimbleWimble. I think it's been in the news and it's got kind of a catchy name, so it sticks around, but I should maybe explain what it is and what its history is. So the origin of MimbleWimble comes from the Bitcoin Wizards IRC channel, when in the middle of the night, one night in August, some person called Tom Elvis Jedusor showed up. This is the name of Voldemort in the French Harry Potter books, so this is just a pseudonym. Showed up on our IRC channel and dropped a text document. It was just some .onion link saying, hey guys, I thought I have this file, you guys might be interested, check it out. So this was some random onion link. We were a bit suspicious, but a couple of us downloaded it and checked, and it was actually just a plain text file with no funny business inside of it. So we rehosted it, and then for the next week or so on Wizards and in person, I spent a while dissecting this and trying to understand what it is and how it worked. And then this was leaked to Reddit. I guess several people reposted the links that the Voldemort guy had posted. And there were some public discussions on Reddit trying to figure out what exactly was being said. And because the original document was written in like Fringlish and it was not very precise or detailed. So we got through all that. We figured out what was going on. I eventually wrote a paper about it, which describes in more detail what MimbleWimble is, how the crypto works, and gives an argument for its security. And that is what I talked about at Scaling Bitcoin in Milan. Since then, I guess about 3 weeks after this, another person showed up on Bitcoin Wizards under the name Ignatius Peveril, which is the name of the character in the Harry Potter books who invented the invisibility cloak. And what Peveril said was that he was working on an implementation of MimbleWimble, and he had started this and he had published it and he posted a GitHub link. And cool, I mean, this is great. I had been hoping to do this and I never found the time, but fortunately, some Harry Potter character usurped me. So this guy showed up. I got a phone call. I was just at home drinking tea in Austin, as I do. And my phone went off, as it doesn't. And it was Brian Bishop. Brian Bishop saying, hey Andrew, get on IRC. This is important. You need to see this. And I'm like, okay, all right. So I went on IRC, and sure enough, here was yet another Harry Potter character showing up doing MimbleWimble stuff, which is like super exciting. I was super jacked. So I went for a long walk. I went for a long run around Austin to let my excitement out. And then over the next couple of weeks, this project continued to work. There are more Harry Potter characters. There's, I think, Grindelwald, the wand maker, has shown up, as well as Voldemort's mom. And this is a continuing GitHub project, which is not something that you can download and run today, but hopefully it will be in the near future. And there is ongoing development. A lot of work is going into this, which is great. I am not Ignatius Peveril, I am not Voldemort, I am not any of these people. I swear you have my word and nothing else, but that is my claim, and I'm sticking to it. So with all this history, I should maybe explain what I'm talking about. The MimbleWimble is a design for a blockchain-based ledger. It is basically a replacement for the Bitcoin blockchain, or a proposal for a Bitcoin-like blockchain. Which could be implemented as a sidechain, where you've got a completely separate chain, you move Bitcoins onto it, you move Bitcoins off of it, but it has its own independent life. Or potentially in the far future, where we've tested this technology and it's proven itself, we could maybe even soft fork this into the Bitcoin itself as some sort of extension block scheme, which would basically be like a sidechain that's integrated into the system. Where MimbleWimble differs from Bitcoin is that rather than having inputs sign the entire transaction, as in Bitcoin, the way Bitcoin transaction is structured, you've got a pile of inputs, you've got a pile of outputs. Every input has a key associated to it, and it has to have a signature of the whole transaction with that key. This is very simple, it's very discrete, it's sort of each input is isolated. MimbleWimble changes this model, and rather than having each input sign the transaction, you sort of create a multi-signature across all inputs and all outputs If you take the sum of all the keys on all the outputs minus the sum of all the inputs keys, you will get an elliptic curve point, which you can treat as a public key. And what that public key represents is a multi-signature public key for all the transacting parties. So for the owner of every input and for the owners of every output. And so a signature on this represents that the transaction was authorized by everybody involved, roughly. So because of this design, MimbleWimble does not support script. So a lot of you are familiar with Bitcoin script. This is what's used to do all sorts of neat tricks like zero-knowledge contingent payments, or TumbleBit, which is a mixing service design that came out of MIT, or cross-chain atomic swaps, or various types of multi-signatures, non-interactive multi-signatures. All this does not work with MimbleWimble, because MimbleWimble works. Rather than having inputs that have some sort of meaningful signature attached to it, the whole transaction needs to sum, and that sum has all of the authentication in it. And it's just a sum. It doesn't have a lot of features. You can't really modify it in a way that would give it more features. Although, as we'll see, there are some hacks you can do to get some of our favorite things from Bitcoin to work. So let's try to be a little bit more precise here. So a MimbleWimble transaction, like Bitcoin, is a list of inputs and outputs. Where it differs from Bitcoin, first of all, is that it supports confidential transactions, which is a scheme developed for the sidechain Elements Alpha to encrypt the amounts of all transaction data. So in Bitcoin today, when you create a transaction, it's clear what all the output values are, it's clear what all the input values are. If you want to check that the transaction is valid, you make sure that the output values equal the input values, plus or minus some fee or something. But you can see all the outputs, you can see all the values, so you can tell that the transaction is valid. What confidential transaction does is it homomorphically encrypts all of the values so that it's possible to add all the output values minus all the input values and verify cryptographically that these add up to 0. And that's all you can tell about it. You can't tell what the individual values are. You can only tell whether or not they add up to 0. And this is actually very close to how I described how the entire transaction works in MimbleWimble, and that's no coincidence. MimbleWimble extends this property of summing the outputs and inputs from just the values to the entire authentication for the transaction. And the way it does that is through this excess value. So every transaction, it has a bunch of inputs, which are referenced to old transactions. It has a bunch of outputs, which are explicitly set. And then it has this difference, which is this excess curve point that I've been talking about, and a signature with this excess curve point. And this is what provides authentication for the transaction. I don't like that explanation, but I'm not sure I can go into any more detail without sort of reciting my paper. This is unfortunately a bit of a technical thing, but the way to think about this is that the excess is a multi-signature key, basically. It's a multi-signature key with the owners of all inputs and the owners of all outputs. So what does this model get you? So here's my beautiful picture of a MimbleWimble transaction. What this model gets you is that if I have two transactions like this, for this transaction to be valid, you need to be able to add up the outputs, subtract the inputs. It should equal this excess value. This property is preserved if I combine two transactions like this. So you can see if I have two valid MimbleWimble transactions and I concatenate them, the result is a valid MimbleWimble transaction. And there's no interaction involved with this. So this is how CoinJoin works in Bitcoin, except with CoinJoin, everybody who's transacting has to consent to it and has to interact, and there's a whole protocol you have to go through. In MimbleWimble, if you have two transactions, you can just paste them together like that. And as long as you preserve these two excess values, the result will be a valid transaction, which is very cool. This is like a non-interactive CoinJoin. But there's more. So you might see in this picture that one of these transactions spent an output from the other transaction. This blue output is actually the input of the other transaction. If my validity condition is that the difference between the output set and the input sets has to equal some value, it makes no difference if I add or subtract the same value as long as I do it from both the inputs and the outputs. So I can drop that blue guy entirely. It's as though that output never existed and the transaction is still valid. So what does this mean? It means that if I create a transaction and I send a Bitcoin to somebody, maybe I send a Bitcoin to Victoria, and then she passes the Bitcoin on to Eric, then if these two transactions are floating around the network, they can be combined And the result will look like I sent a Bitcoin to Eric. But this doesn't mean that Victoria's participation was completely removed. There's no evidence of it. Then nobody can prove that she was involved. But this excess value from her transaction remains as part of the transaction. And that excess value still has her signature on it, which means that this could not take place without her consent. So the authorization is preserved, but the evidence of the intermediate steps in this chain of transactions are not. So we can take this to an extreme. We can say within an entire block, we'll just combine every single transaction. So now a block is a list of inputs, a list of outputs, and a list of excess values. It's actually the same as a transaction, which is very cool. And what does this mean? It means that if I have a whole blockchain like this, I'm not sure why this is showing up this way. It doesn't. Okay, I'm going to switch to this view, sorry, for a couple slides so that I can see my entire blockchain. So if I've got a whole chain of blocks, each block is its own transaction. Now imagine that somebody is joining the network for the first time. Imagine MimbleWimble has been running for a year, there's been a whole pile of blocks, every block is itself a transaction, and somebody joins the network and they say, hey guys, what's going on? In Bitcoin, when somebody does this, they need to do what's called an initial block download. They need to download some 90 gigabytes of data, verify it. They basically need to play every single transaction forward. They need to verify all the signatures, at least past however far back they're willing to trust that the signatures are valid. They need to check for the effects of every single transaction took place correctly in order to determine the current state of the chain. But as I hinted with this example where there are transactions floating around and we were able to delete an intermediate state, we can actually do this for the entire blockchain in MimbleWimble. So a new participant does not need all of the data. So let's take a look at what this looks like. Here's my whole blockchain. I can give this new verifier the combination of every single transaction that's ever occurred. Okay, that's nice. But now look at which inputs come from old outputs. It's actually every single input comes from an old output, except for these white ones, which are Coinbase inputs, which aren't real inputs. They're just like a plus 50 or whatever that goes into the block to pay the miner. So every single input can disappear, as well as every spent output can disappear. So this new verifier needs the following data. They need the chain of headers, showing that this is a valid blockchain. They need the list of unspent outputs, and they need these excess values, however many there are for every single block, which is way, way less data than it would be if they had to download the whole chain, which is especially exciting because we managed to get rid of a ton of outputs. And outputs in a confidential transaction scheme are pretty big, and they take a little bit of time to verify. There's something like 2.5 or 2 kilobytes, depending on how you implement them and how large a range you want to hide and various parameters you can tweak. But they're much larger than typical Bitcoin outputs, which are on the order of 30 or 40 bytes. So being able to get rid of those is huge. This is a big win for scalability. And it's also a big win for privacy if this is structured properly. Because you can see in this remaining data, there is very little left of the original chain. All of these excess values are still floating around, which means that every single transaction that ever occurred is there in the history. You can't lie to somebody. You can't pretend that a transaction didn't happen unless you go back and rewrite the block that it occurred in and like fork the chain back to that, same as Bitcoin. But the only reason you can't do that is because this little 32-byte excess value is hanging out in the blockchain. You don't need the whole transaction. That's what's exciting about this, is that we've preserved Bitcoin's security model without having to keep all of the data around. So you can't rewrite transactions without rewriting blocks, which is very good. So let me try to say again what I just said, because this is very important. And I've changed a lot of stuff, and I've deleted a ton of data, and I'm claiming that I am preserving the same trust model. I continue to claim that, and this is weird. Here's why. So what does it mean for a transaction to be valid? It means, first of all, that it's not creating or destroying any coins. In Bitcoin, you've got a fee, which goes to the miner, and the net is still 0. In a confidential transaction chain, you might structure this in some different way, but the point is you can't print money and you can't destroy money without sending it to somewhere that's unspendable or something like this. The transaction has to balance. Secondly, any inputs that go into a transaction are outputs of all transactions. They have some owner. That owner needs to sign off on it, right? This is a transaction network, not a, I'm going to give you whatever you want, and it doesn't matter who had it before network, because it's hard to structure an economy based on that, is all I can say. So we preserve this. I mentioned the excess value is a multi-signature of all the input owners and all the output owners. So in particular, all of the input people, all of the inputs are signed off on. And secondly, we preserve this non-inflationary property, just using confidential transactions. We can add up all the encrypted outputs, we can subtract the encrypted inputs, and we can check that the result adds up to zero value. And in fact, the excess value does this. It's actually two things at once. It's a multi-signature, and it's also a proof that the transaction adds up to zero at the same time. And this is by sort of a neat cryptographic trick of confidential transactions, which is that if you have a commitment to the value 0, you can create a signature with that commitment as though it were a public key. And you can't do this for any other value. So 0 is special. And if you see a signature with a commitment, you know that commitment is 0. So we can exploit that and kill two birds with one stone here. So now let's look at what happens when we put these transactions in the blockchain. We really want, like in Bitcoin, to say that once a transaction appears in the blockchain, that transaction cannot be removed or deleted or reordered or whatever without replacing that block. And then in addition to that, we have a bunch of infrastructure around this to make sure blocks don't get rewritten with any frequency, and then it becomes very difficult to rewrite old blocks and all this good stuff. But what we want is that a transaction being in a block means that transaction is as good as that block, basically. So we want to preserve that. And in schemes where you delete data from old blocks, this can be very difficult to preserve. So for example, one idea you might have to try to reduce the amount of data in the blockchain would be to say, well, what if we just threw out blocks that were old enough, let's say. And every block we will commit to the current state of the network, but once blocks get old enough, we'll just throw them away. So new users come in, they download the last 3 months of the Bitcoin history. And starting at the beginning of that 3 months, they see a commitment to the state of the chain 3 months ago, and then they play every transaction forward from there. And this will save a lot of space because we've just thrown away a ton of data. But this does not preserve Bitcoin's security model. The reason being that somebody with the hash power to rewrite 3 months of work is then able to replace any transaction that happened before that 3 month point. There's sort of this cliff, a so-called incentive cliff, where somebody who is strong enough to rewrite 3 months less a day can rewrite 3 months less a day worth of transactions. Somebody powerful enough to write 3 months worth of transactions can rewrite all of them. So there's a strong incentive for somebody who's already attacking the network to attack it just a little bit harder and get a huge payday. MimbleWimble does not have this problem because all of the block headers, the entire blockchain remains in play. What gets dropped are just the explicit full transaction contents. And here's my picture again, which I don't think is very helpful here, but I put it there because it fit. So here we go. So this is roughly what I said. What data do you need in total? You need the block headers, you need unspent outputs from every block, and you need these excess values. That's it. That's the entirety of the data. For the unspent outputs, you also need these range proofs. And this is something I haven't mentioned explicitly, but this is the bulk of a confidential transaction output. What it is a proof that the output, although it's encrypted, does not represent a negative value or some value that can act negative when you add it to other values. The concern here is that the homomorphic encryption that we use, the homomorphic commitments, are vulnerable to overflow. There is some value that you can think of as -1, which you can use to inflate the currency if you did this in a naive way. If you just homomorphically encrypt everything, what I can do is I can take some Bitcoin transaction, I can put no inputs at all into it, then I create a -10 Bitcoin output and a 10 Bitcoin output. And this, of course, will add up to 0 if you add everything up, but I've created 10 Bitcoins out of thin air, which is very bad. So the way we solve this is with the range proof, which is part of confidential transactions, and it's preserved in MimbleWimble, because MimbleWimble is a sort of an extension of confidential transactions. So what does this look like? So I'm going to give numbers from the Voldemort scheme that was posted on Wizards, although I can improve this a little bit. In Bitcoin, there are 150 million transactions, leading to 40 million transaction unsigned outputs in the end. So This is 21.6 gigabytes of historic data for a MimbleWimble chain doing the same thing. What the historic data is the block headers and these excess values. Basically 150 million excess values is mostly what that is. 2 gigabyte of actual UTXOs, and then 100 gigabytes of these range proofs. So you can see they're really the bulk of the data. For 2 gigabytes worth of UTXOs, it's like a 50 times expansion in the amount of space needed for the range proofs. So this doesn't look great, does it? I mean, I'm talking about 130 gigabytes for a Bitcoin-like system. And Bitcoin, we know, only takes today like 90 gigabytes. So maybe that's not an improvement. But consider that MimbleWimble supports confidential transactions. And then this looks much more impressive. Because in Bitcoin, if we just added confidential transactions and we'd had it from the beginning, having every single output have this 2 kilobytes of extra range proof data would lead to a total blockchain on the order of a terabyte. So this is actually a massive savings already versus Bitcoin with confidential transactions. Secondly, the rate of growth in this scheme is proportional to the number of UTXOs that are floating up there, the number of unspent outputs, not the total length of the historic chain. Meaning that if somebody creates a transaction that spends a pile of outputs and only creates a couple of outputs, then that transaction will actually shrink the blockchain from the perspective of the new verifier, which is very cool. It means we don't have this forever increasing. I mean, we may in practice, but it's not necessary for things to forever increase. And we can, in fact, incentivize the chain not to grow too wildly. You could say that there's a limit on how many UTXOs exist at any given block height, for example. And then people would be incentivized to save fees or even to get negative fees to reduce the size of the UTXO site, which is very cool. And that would lead to a blockchain which is bounded in size. Secondly, there is a bit of cryptography we can use to shrink this. And I will come back to this near the end when I'm talking about future research. But these numbers are not the be-all and end-all. Oh, okay, so next slide. First, before I talk about any new crypto, let's talk about where are we going, mainly with Grin. So this Peveril guy who showed up saying, I'm working on this MimbleWimble implementation, his implementation is called Grin. And you can find this on GitHub. So right now, the main focus is developing this, is doing for the most part, simple infrastructure stuff. Setting up a peer-to-peer layer, figuring out encoding, setting up all the crypto that we need. Just not really researchy level work, just continued development work. And a fair bit of that needs to happen before we have something that we can show and give to people and people can play with. Part of that is nailing down these chain parameters. And then finally, I have been talking since the Voldemort paper came out about implementing MimbleWimble as a sidechain, or maybe in the far future as some sort of extension block. The design philosophy of Grin is to be as simple as possible. And what that means is that right now it's implemented as an altcoin, which I'm not very thrilled about. There's a pile of problems with this, not least of which is that if I was involved with this, it would mean that I was issuing securities, and I'm kind of scared of the legal implications of that. But then it's also you've got to bootstrap a new economic system. You need trusted exchanges. It's slow and it's difficult and risk-prone to move into it. So what I'd like to see is more research going into extending Grin to be a sidechain, and even be a sidechain as well as an altcoin. So you have a single chain that supports multiple things. And that's something that I'm doing continued research on. And I have some cryptographic tricks that I think can be used to support this in kind of an exciting way. I have submitted a paper to the Financial Crypto 2017 conference that talks about this in more detail. But for now, that's all I'm going to say. I have some tricks up my sleeve that I'm very excited about, and hopefully I'll be able to come back here and talk about it when the time is right. So that's the state of play today. That's where we're at. Let me talk a little bit about some open problems, because there's a pile of new crypto here, and there's some fun problems for those of you who are mathematically or cryptographically inclined. The first one I want to mention is unconditionally sound commitments and range proofs. So this is a general problem with confidential transactions, which is if the underlying cryptography were broken, which it means something like NSA revealing that they have broken all of the crypto in the world, or a quantum computer, or something like this, The consequence for confidential transactions today is that this could allow amounts to be forged. It would basically allow inflation to happen, where somebody could commit to some amount, make sure it all is up to zero, and then later open it to reveal that it was actually a much bigger amount. What we would prefer is if this were not possible. We would prefer, in the case of a mass crypto break, we would rather privacy be harmed, but soundness and inflation freeness is not. And that there is an inherent trade-off here between unconditional soundness and unconditional hiding. And you can prove that you can only get one. Right now we have unconditional hiding, which is, I mean, that's cool, I guess. But we'd much rather have unconditional soundness. And actually, since I brought this up, I was talking to Dan Bonet at Stanford a couple days ago, and he showed me a scheme that actually achieves this with about a 20% space hit, which is pretty good. I think 20% is pretty small for the magnitude of the cryptographic assurance that it gives us. So that's cool. I guess that's not an open problem anymore, but it's still a fun one. What is an open problem, though, is getting rid of this 20%. Trying to make these things smaller. Can we make range proofs smaller? What if we have a pile of range proofs? Can we make the pile smaller? So this is aggregate range proofs. This is something like somebody's verifying a block, and the block has 1,000 outputs, and every output has some range proof on it. And what if, by making every range proof be like 10 times bigger, it was possible to make 1,000 of them much smaller? And this is something we can do in a small way with regular digital signatures. This is something that we've been in the news a little bit of a research direction for Bitcoin aggregate signatures to shrink the size of Bitcoin blocks. It's an open problem if we can do this for range proofs as well, because range proofs are a fair bit more complicated and intricate than signatures. But if we could aggregate them, that could be a huge space savings right there. Because as we know from the numbers that I gave earlier, the range proofs are far and away the bulk of the data and the bulk of the validation time. So there ought to be something here. I mean, you've got like, millions of mostly the same thing. Often there's a shortcut. Another open problem that I didn't talk about too much, but this is something that Grin is facing right now, is how do you design a peer-to-peer protocol where it is possible to just combine transactions freely? It turns out that if you just allow free combination of transactions, this causes quite serious problems in the peer-to-peer layer, even without anybody griefing anyone or anybody trying to cause denial of service attacks. And an example of this is, suppose I'm some privacy-minded user and I'm trying to send a coin to Victoria, but I don't want anyone to know that this is happening. So I might wait for some other transaction to come along, and then when that transaction comes along, I'm going to combine my transaction onto the one that I just saw and broadcast the combination to the network, right? Sounds reasonable? Well, what happens if I do that and somebody else has the same idea? So now I've got this combination that has my coin going to Victoria on it, and another transaction which conflicts with the first one, which is missing my part but has somebody else's part on it, right? And everybody's just doing the sensible thing. They're just trying to merge onto whatever floats by them. And the result is two transactions floating around the network that conflict, meaning that only one can get confirmed. So this is pretty bad. So it appears that in practice, we need something different, something probably a bit more complicated than just a simple flood network where people are combining, willy-nilly. And what this might look like is, for example, people sending their transactions directly to miners. And maybe they give a variant of the transaction to every different miner. And eventually one miner will get it. The other variants are invalid, that's fine. And then one miner knows what the original transactions in that block were that they combined, but nobody else does. And the result is pretty good privacy and a fairly simple model that's fairly easy to reason about, although it does involve having some sort of communication channel with miners, which itself is a bit complicated. A final thing would be quantum computer resistance. So I talked about unconditional soundness, which is a step towards this, where in the presence of a quantum computer, people lose their privacy, but hopefully on just old data, hopefully by then we've moved on to something different, but the system is still sound. We can do better than this, I think. We ought to be able to do better than this. There's a whole field of cryptography devoted to developing new cryptographic primitives that do not break in the face of a quantum computer. And I know how to replace large parts of MimbleWimble with quantum hard analogs, but I'm missing a couple things. The big thing that I'm missing is the range proofs themselves. But our friends at Stanford claim to me that such a primitive exists, and they just need to search the literature. So maybe this also is not actually open, but to me it's open. In my heart it's open. Yep.
On the merge conflict, would something like a software transaction model make sense in this case?
Sure. So the question is, to deal with these merge conflicts, is something like software people memorizing transactions that come by, will that fix it? Not entirely, no. You may be able, no. So in the example I gave, where I attached my transaction to one that was floating by, nobody knows my original transaction there. And so if that transaction itself was a combination, there are transactions where nobody even saw it, where the original transaction did not even exist. So that's not a complete solution, unfortunately. Yep. The question is, am I making a signature of all the other signatures? And no. When you aggregate these transactions, there's a signature hanging off of these excess values, and every individual excess value stays separate, and every individual signature stays separate. Although we can aggregate these signatures. So we can compress the combination of all the signatures, but they still remain independent, separate signatures. And actually, since we're doing questions anyway, I should end the talk. So this is my talk. If there are more questions, I'm here.
How many transactions?
Can you guys wait for the mic?
Oh yeah, that would be. Thank you.
I'm sorry for interrupting, but how many transactions can you do per second?
So in real time, MimbleWimble does not give you any compression. It gives you compression on disk, it gives you compression when bootstrapping new nodes, but in real time, you've got these full blocks of full transactions that everybody needs to validate. And beyond that, these are transactions that they're confidential transactions, so every output has some range proof hanging off of it. I don't have numbers for you, but they're not good. They're not as good as Bitcoin, for example.
So if I have 1 million transactions per second,
MimbleWimble will not help you with this. Yeah.
I had just a question from your paper online. It says that MimbleWimble shrinks the transaction history such that a chain with Bitcoin's history would be 15 gigabytes. We solve this and combine it with existing research for compressing proof of work blockchains to reduce this 15 gigabytes to less than 1 megabyte. So how did the less than 1 megabyte compression, is that accurate or?
That is accurate. That is more than my existing talk in content, but I can say briefly that the signatures that are on every excess value, I have a way to combine all of the excess values and all of the signatures within a block. And beyond that, I have a way to remove entire blocks from the chain, like intermediate blocks along parts of the history, using something called compact SPV, which is described in a recent paper called Proofs of Work, and also in an appendix of the Sidechains white paper a couple of years ago. And what this gets you is a blockchain that maybe was originally hundreds of thousands of blocks, now compressed to less than 1,000 blocks. And inside each block, there's only a single signature, or maybe there's logarithmically many signatures in the size of the original chain. And that's what gets you this massive savings, is that you can compress out the vast majority of entire blocks. But that involves quite a bit of new crypto and much more serious assumptions than just normal MimbleWimble requires.
Andrew, I wanted to congratulate you on coining the phrase massively prunable. I think that has incredible meme potential, and I hope the internet takes that and does creative things with it.
Thank you.
But my question is, one of the benefits you talked about is being able to prune the blockchain and be able to reduce the size. Do you have any thoughts about when size of blockchain is actually going to become a problem?
No, I do not. Yeah, there's an ongoing debate about capacity limits and how we can improve this capacity limit of a globally scalable, distributed database that can't be reversed. And I have no thoughts about the practical requirements there. But it's good to have more. It's good to have more capacity. That's it.
Would it be possible for MimbleWimble to assist in, let's just say that you were able to reduce, or I'm not sure if this is possible, but let's just say you were able to reduce, or I'll ask this, is it possible that with MimbleWimble you can reduce the UTXO set and improve sharding capabilities there? Because right now sharding is out for UTXO. Is it possible that MimbleWimble could fix that?
No, MimbleWimble probably actually makes this worse.
Okay.
So the problem with...
Okay, yeah, because you need the range proofs too?
Yeah, exactly, because of the range proofs. The problem in MimbleWimble is even if a single output anywhere ever had a negative value, the whole chain is now at risk. So you really need to know that every single output is positive.
What are the cryptographic assumptions required, maybe in comparison to other projects which try to achieve similar things, and how long does it actually take to verify and create a MimbleWimble transaction?
Sure, thanks. The cryptographic assumptions for MimbleWimble are that the elliptic curve discrete logarithm problem is hard. And that's it. And these are the same assumptions that Bitcoin has. There are actually no new cryptographic assumptions in MimbleWimble. So that's certainly a very good thing. And as far as creating a MimbleWimble transaction, this takes as long as producing range proofs for all the outputs. So on the order of milliseconds. I don't have exact numbers. I do, but I don't remember them. But on the order of milliseconds. Yeah, okay. Peter's nodding, and he also has these benchmarks. So other projects that do similar things, well, two that come to mind are Monero, first of all, which blinds the identity of the inputs in all of its transactions. And Monero, I think, also has no new cryptographic assumptions, but its scalability is not as good, and its transactions are similar to create. The other one that's been in the news lately, of course, is Zcash. The cryptographic assumptions underlying Zcash are much, much more taxing than they are for Bitcoin. So they use a elliptic curve that supports a pairing operation, which is some extra algebraic structure that the curve has to support for their cryptography to work. In addition, they require some technical properties of this pairing to hold. There needs to be some hard problem related to this pairing. I actually don't know specifically what it is. And then finally, they require a trusted setup. So initializing the system parameters involves some secret key data, what they're calling toxic waste, where if anybody had that data, they could silently inflate coins. And MimbleWimble has no such thing. And then as far as creating transactions, I'm not sure. I've heard numbers for the confidential transactions that they create on the order of 20 or 30 minutes. So it is significantly higher than it is for something like Bitcoin or MimbleWimble, or even Monero, where it's pretty much an instant thing.
Hey, so the aside about the signature for the commitment to zero was like what I was missing in terms of understanding how the access worked.
Oh.
So that was very helpful.
Okay, thank you. I will remember that.
Yeah, it would be nice to have that in the paper.
Okay, yes.
Would you comment a little bit on, you mentioned tricks to make smart contract stuff work?
Oh, yeah, I forgot that. Yeah, absolutely. So a big thing is time lock transactions. So it is possible to create payment channels, not very featureful payment channels, but payment channels that work, using nothing but multi-signatures and lock time transactions. So the way the multi-signatures work in MimbleWimble is that these range proofs on the output, these range proofs assert ownership of the output, and it's possible to create a range proof interactively with a multi-signature. You can create an M of n range proof, although I haven't written the code. Nobody's written the code for this, but it's mathematically possible. So MimbleWimble sort of inherently supports multi-signatures, although interactive multi-signatures, unlike Bitcoin's where everybody signs and sign and pass along. There's interaction involved. As far as lock times, this is much simpler than multi-signatures. The way this works is the excess value signs the minimum block height, sorry. Every transaction has a minimum block height, and it's not allowed to appear in the blockchain until after that, and the excess value signs that. The excess value is a multi-signature, so that means everybody signs off. So now the excess is doing a third thing, I guess, which is enforcing lock times. And then once you have multi-signature and lock times, you can create single hop unidirectional payment channels, which is a building block towards some sort of off-chain payment system, although it's a very small part.
I gave away my mic, but does that break syncing signatures?
The question is, does this break syncing signatures? Yeah. So this is part of the reason that I didn't talk about syncing signatures this time. That's a very good point. In addition to them being like a massive amount of complexity, and they also require a pairing assumption, which currently is not involved, they also break my payment channel design, which is pretty serious, and potentially would be a net bad for scaling. Even if I get this 1 meg of compression, if you can't do off-chain stuff, that's not great.
So I'm sure that I don't have my head all the way around this, so maybe this question will help me, I'm not sure, but is the anonymity that you talk about a product of the netting of the inputs and outputs? Is it exclusively a product of that? So if there were only one transaction in a block, would there be no anonymity?
About half. So there are two pieces. One is, as you say, the netting of the transactions. And this is why we would prefer to have a peer-to-peer label layer where things are not being broadcast to everybody and so forth. So yes, if there is only one transaction, that's going to look like there's one transaction and everyone knows, all the inputs of that block correspond to all the outputs in that block. But another part of MimbleWimble's privacy comes directly from confidential transactions and not having scripts. So I mentioned in my abstract, I said outputs have no hair. What this means is that every single MimbleWimble output looks like a uniformly random curve point and has no other features to it. So you do retain the transaction graph in degenerate cases, but this transaction graph has much less information than it does in the Bitcoin case, because your outputs no longer have amounts, they no longer have scripts. That's it.
So one more question, since I still have the mic. You've talked about both the anonymity and you've also talked about the block sizes. So what do you view as the strongest feature of MimbleWimble? Is it one of those or something else? Or is it, what makes it compelling?
I think right now the scaling, because the scaling I know how to do. It does not involve peer-to-peer architectures and stuff that I've never touched and would require people smarter than me to step in and hold my hand through it. But they're both pretty compelling. So.
Do you think that the required communication with miners that you were alluding to in certain situations, like how serious do you think that is a trade-off? To me, it kind of seems like a big trade-off.
It's a big trade-off if you've got very few miners, but it's not as bad as it sounds if you were to naively do this in something like Bitcoin today, for two reasons. One is that you can have miners broadcast how to contact them inside of blocks and stuff, so there's no central directory. You could also have central directories. You could have multiple central directories or something like this. Secondly, it's possible in Bitcoin today, but not very common as far as I know, for individual miners, meaning the people holding the Asics, to completely define the contents of a block, rather than the mining pool, of which there are very few, defining the contents of the block. And the way this would work is something like the people who create the block, when they submit shares to their pool, rather than having the share be a hash of a known block, the share is a hash of some arbitrary block that the miner created with a Merkel proof showing that it pays out the pool. So the pool knows that it's getting its money, they don't know anything else about the block, and this way you have much, much more decentralization of what transactions go into blocks. And in particular, you can communicate transactions to small miners around the world. And then you get much more privacy from that. Because if you've got 10,000 or 1 million miners or something, and you communicate to some random collection of them or to all of them or something like this, you give them all different transactions that are secretly the same transaction, but you can tweak them so that's not visible. Then the resulting block with high probability nobody will know what original transactions went into it.
Any more questions?
So you can create an alternative currency to Bitcoin with this.
It's possible.
It is possible.
Yes.
And scaling is the main significance of this.
I guess so. I mean, the privacy, there's a lot to
Or
this.
anonymity.
Yeah.
Or anonymity.
If you're asking me to say which is better, scaling or anonymity,
Peanut butter and jelly.
yeah, I mean, exactly, they go to bed.
One without giving up the other.
That's a good point. Peter just said you get one without giving up the other, and that's huge. And there's usually been a trade-off historically in systems where you can get great scaling by giving up a lot of either decentralization or privacy, or you get great privacy by giving up a lot of scaling. And here we get both in one package, which is really the exciting part.
So when you get a side chain, right? Is there any limit to the size of the side chain?
Only the resources of the people validating it. That's the best answer I can give.
What is the best application for this?
So MimbleWimble, because it does not have scripts, basically supports only one application, and that is transferring value between parties. Simple transactions where somebody is sending money to somebody else, or some collection of people is sending money to some other collection. Bitcoin can do all sorts of cool and neat things because it has scripts. So it can do things like zero-knowledge contingent payments, which is a trick that, who did this now? I'm blanking. But this is Sean, thank you. Sean Bowie presented this. He sent a Bitcoin or a test Bitcoin to Greg Maxwell in exchange for the solution of a Sudoku puzzle at Financial Crypto 2016. And this was entirely on the Bitcoin blockchain. The Bitcoin blockchain enforced that Greg actually gave the solution. So that's a neat trick. I mean, you can't do anything like that in MimbleWimble. You also can't do cross-chain atomic swaps. You can't do lightning channels, the multi-hop, hash-locked, crazy magic lightning. You can do payments between people. Simple payments is the answer.
So the quantum network is an enemy of yours or it's an advantage?
The question is, are quantum computers or quantum network an enemy or an advantage to the system? And the answer right now is that they're an enemy. The quantum hard systems that I know about are much larger. The scaling is much worse. The amount of data is larger by some large constant factor. I don't know that that's necessarily has to be true. Maybe it's possible to shrink the range proofs or to aggregate range proofs or something with quantum hard crypto systems, and it turns out that it would be a massive boon if people were looking at this. I don't know. But where it stands today, it's firmly in the this would be bad kind of camp. But there's no reason that should be the case, and it's just a matter of research to get a better answer.
One more question.
I mean, this is more philosophical than the technical part of it. Does that mean that we can curb inflation with these type of transactional exchanges?
To the same extent that you can curb inflation with Bitcoin. So when you define the scheme, if you were doing some sort of altcoin like in Bitcoin, you define a clearly well-defined inflation schedule. If you have a sidechain or something like this, then actually you just copy the money supply from Bitcoin. And you can't really affect the money supply at all in that respect if you're just using some other token that exists already. So MimbleWimble offers no new advantages over Bitcoin in that respect.
Okay. Thank you, Andrew, for your awesome talk about MimbleWimble.